Excuse me. Welcome to my new calculus site. My name is John Gabriel, and this is another in a series of lectures. In fact, it's going to be lecture 8, in which we discuss the problems with misguidedness and mainstream ideas of rigor. So let's begin. Now, excuse me, we've seen in the previous chapters quite a few topics. We began right at the beginning for what it means for a concept to be well-defined and some mainstream misconceptions and the fact that there are no actions or postulates, and I proved that by deriving everything from nothing in that chapter. I also gave you the perfect derivation of number in chapter 5, and how we got algebra in chapter 6. Finally, I demonstrated to you that without the arithmetic mean, you wouldn't have had calculus or anything today. And in this chapter, chapter 8, we discuss the lack of rigor in mainstream calculus and its flaws. So let's go to chapter 8. Excuse me. Now, you may have heard of Judith Grabiner and that piece of crap she wrote called The Origin of Cauchy's Rigorous Calculus. Now, Judith Grabiner has a PhD in mathematics. She earned that, obviously, through some dissertation, and I wouldn't even bother reading it because, as you can see from her book, she really doesn't know any mathematics, and you'll soon find out that the book actually has zero value. So she starts her preface with this. Augustin Louis Cauchy gave the first reasonably successful, rigorous foundation for the calculus. You know, that nonsense has been repeated so many times, it's now believed by every Tom, Dick, and moron. Beginning with a precise definition of limit, he initiated the 19th century theories of convergence, continuity, derivative, and integral. And that's all false, as I'm about to prove to you. Now, neither Cauchy nor anyone else provided a rigorous formulation of calculus before I produced the first and only rigorous formulation in human history. Now, of course, more advanced alien civilizations may already know of it. The problems with calculus had nothing to do with a precise definition of limit, which is non-remarkable, even if there weren't one, because neither the derivative nor integral require the limit concept or related theory, as has been proved in the new calculus formulation, and which is to be demonstrated in the chapters to come. The misguided and deceptive story of rigor began with Cauchy's definition. He used questionable or ill-formed terminology, such as finite value, infinity, infinitesimal, limit, infinitely small, and decreases infinitely. Yes, those were the actual expressions that Cauchy used. So he said, when the value successively attributed to the same variable approach indefinitely a fixed value, eventually differing from it by as little as one could wish, that fixed value is called the limit of all the others. So we continue to note that the fact that a value of a difference quotient or some partial sum of a sequence is a magnitude is proved by convergence, even without knowing anything about the limit, which is the value being investigated. Okay? So, for example, it's certainly untrue that one can make it differ by as little as one could wish, because if one wishes no difference, then this is not possible. In the cases of incommensurable magnitudes, that is, magnitudes that are incommensurate with any others, such as pi, e, or square root 2. The famous mathematics historian Carl Boyer had this to say. read this whole quote here and take note of this statement in the second paragraph. That is, one cannot define the number square root 2 as the limit of the sequence 1, 1.4, etc., because to prove that the sequence has a limit, one must assume, in view of the definitions of limits and convergence, the existence of this number as previously demonstrated or defined. Did you get that? Read that again. Now, Boyer was the only one before me to notice that. And the next line is a killer. Cauchy appears not to have noticed the circularity of reasoning. He doesn't appear. He didn't notice the circularity of reasoning in this connection, but tacitly assumed that every sequence converging within itself has a limit. Okay, and that's in Boyer's publication, excuse me, The History of Calculus and Its Conceptual Development. Now, only Boyer realized the circularity of Cauchy's arguments before me. Oddly enough, no one else in the mainstream seemed to notice. Now, Cauchy also tried to define an infinitesimal. He said, when the successive absolute values of a variable decrease indefinitely in such a way as to become less than any given quantity, what on earth does that mean, less than any given quantity? That variable becomes what is called an infinitesimal. Still, all hand-waving nonsense. Such a variable has 0 for its limit. As far as Cauchy was concerned, an infinitesimal is actually a variable expression rather than an actual number, which becomes very small. So small, in fact, that it is less than any given quantity which is greater than 0. To believe this, you need faith that there is a number that immediately succeeds 0 and is less than every other number. Of course, that's absolute rot. The singular is plainly absurd, but mainstream academics such as Abraham Robinson have succeeded in creating special subsets. They're also called ultrafilters in his theories of the interval 0, 1, in which only infinitesimals can reside. But don't ask where the infinitesimal numbers begin and end, because that's a heresy, and you can be excommunicated from the Church of Academia. The infinitesimal, like its older sibling infinity, is clearly and provably a rubbish concept which has no place in mathematics or any other field of rational thought. Some of Cauchy's colleagues and compatriots knew this, and the struggle for rigor continued. Now, Cauchy's definition of continuity is this. He said, let f of x be a function of a variable x, and let us suppose that for every value of x between two given limits, this function always has a unique and finite value. Wow. If beginning from one value of x lying between these limits, we assign to the variable x an infinitely small increment h, an infinitely small increment h, whatever nonsense that is, the function itself decreases by this difference, okay, that difference, which depends simultaneously on the new variable, which is h, and it also depends on the value of x. And then he carries on and he says that f of x will remain continuous with respect to x between the given limits if between these limits an infinitely small increment of the variable always produces an infinitely small increment of the function itself. In other words, a total load of crap. Now, pay attention here. This total load of crap is what led to Cauchy's, to Weierstrass's definition of continuity. And this is what you see as a definition here for continuity in mainstream calculus, exactly as you see it here, where L is the limit at the point C. Now, if L is not a rational number, then L is denoted by some symbol, in this case by itself. And the difference cannot be 0 for any imagined f of x. However, it is required in the modern definition that f of c is equal to L. That's how this very definition works. In addition to this statement here, so the first order logic statement, which you see here, takes care of this requirement because no condition is placed on either epsilon or delta with respect to being greater than 0. So the web of ignorance becomes more intricate when the limit is formally declared. And the only difference between this statement or definition in quotes, because it's not a definition, it's a definition, and this one is that we require the distance to be greater than 0. And there's a very subtle reason for that, and we'll see it in a moment. Now, modern academics need holes in functions to justify this definition here, because they want the limit to exist even if it isn't defined there. However, they make an exception in the case of the derivative. Both the limit must be defined and the function must also be defined there. The derivative function must be defined there. Since the application of this results in the statement where delta f of xh is equal to this difference quotient, they erroneously think they are safe from having assumed that L is in fact the limit or the required derivative f prime of c. Now, one academic called Professor Muckenheim thinks that the Cauchy criterion rigorizes calculus, but this is obviously false because verifying a sequence converges to some limit does not tell us how to find the limit in a systematic way, as is the case with the derivative definition in terms of limits, okay? So ultimately, what's happening here, you can read this chapter and there will be a link to my free ebook, but the way this buffoonery works is the difference quotient is defined as follows, and it reduces to f prime of x plus some expression in x and h, whatever it is, or any combination of x and h. Ultimately, this expression must be 0 in order for the derivative to be calculated. So it is required not only that this is equal to 0, which is only possible if h is equal to 0, but that this difference quotient be defined at 0, 0, which is impossible. So in other words, you need f prime of x plus 0. Any astute reader will immediately see that the first principles method is a kludge, and it was contrived by Cauchy and sold to the mainstream by Weierstrass. Thus, we can conclude there is no systematic way of finding the derivative in mainstream calculus. It's a kludge, okay? So what you have to do first is divide by 0, perform all sorts of legal arithmetic, and then right at the end, set this expression q of x of h back to 0. This illogical thinking and ill-formed reasoning didn't stop with the derivative. It was carried through to the definition of integral too. And I show you here that their integral is actually equal to the integral itself plus some remainder in x and h. In fact, in the new calculus, you won't find any of this monkey business. So what I've done in this chapter is also given you some background and dismissed the ill-formed notion that there are piecewise functions. There aren't, because in mathematics, a function is a relation between a set of inputs and a set of permissible outputs, with the property that each input is related to exactly one output. Ignoring the fact that a set is an ill-formed concept without any definition, the above statement would rule out the ill-formed concept of piecewise function, because a piecewise function contains more than one set. So a function with a discontinuity is not considered to be a piecewise function. Calculus does not generally apply to functions that have discontinuities or are not smooth over a given interval. So there are holes and more holes. In mainstream academia, one can define a new function simply by multiplying by 1 and punching a hole in the function at k, at x is equal to k. And I've explained the reasons why they need this, because the very definition up here would fail if there was not the stipulation. Let's have a look here quickly. The stipulation that delta is greater than 0 and epsilon is greater than 0. Okay, it would fail. So they need holes in their functions. Well, that's what I've tried to express over and over many times to mainstream academics in the past, and it just doesn't seem to sink into their stupid heads. It is a myth that any function has a limit at a given point without being continuous also at that point. Okay, it's a myth. Multiplying any function by 1 does not change the function rule, which is based on one set relation, not many as erroneously believed by mainstream monkeys. More absurd is how mainstream academics can proceed to multiply by 1 and then find it unacceptable to divide by 1, thus arriving back at the original function. Okay? So these misguided ideas have infected mainstream calculus to such an extent that students have to learn nonsense like this. Okay? We don't need this part here. Sine of x over x when x is equal to 0 is equal to 1, because this is not the irreducible form. The irreducible form is given by this expression here. And if you plug a 0 into all these x's here, you get 1. So there is no need for a limit. Last but not least, it gives incompetent mainstream calculus teachers more impetus to design meaningless exam questions involving limits and derivatives on piecewise functions. And I promise you, you can believe me or not, but none of this crap that you learn will ever be used anywhere outside of your real analysis class. So before we learn the new calculus definition of integral, let's understand what the mean value theorem says. And that is the next chapter, which I will go over once again in another lecture. Hopefully in the not too distant future. Well, this is a new calculus channel. I am the great John Gabriel, discoverer of the first and only rigorous formulation, and I trust you've enjoyed this presentation and will join me again at some future time. Till then, goodbye.